Hello everyone, and welcome to my presentation on sea level equation. Global sea level rise is one of the clearest indicators of climate change, reflecting both the melting of land ice and the thermal expansion of seawater as the planet warms. Even a small increase in sea level can lead to more frequent coastal flooding, land loss, saltwater intrusion, and the displacement of coastal communities, especially in low-lying regions and island nations. Understanding and predicting these changes is crucial for the adaptation and long-term planning. The sea level equation provides the physical framework that links ice mass loss, ocean expansion, and the Earth's gravitational response, allowing scientists to understand the different factors driving sea level change. This slide shows the oceanographic form of the sea level equation. On the left-hand side, we have the rate of change of sea surface height, denoted as d eta over dt. This is the quantity measured by satellite altimetry relative to a reference salt. The right-hand side of this equation is made up of three main terms, each representing a different physical process, first of which is the eustatic term. The eustatic term represents changes in the total mass of the ocean water. For example, when ice sheets or glaciers melt, they add more water to the oceans, therefore changing the total mass of the ocean water. The second term is called the steric term. This accounts for changes in the density of seawater which occur when the ocean warms or cools, or when salinity changes. Warmer or fresher water expands, increasing sea level, while cooler or saltier water contracts. The third term is the isostatic term. It reflects vertical motion of the ocean floor, for instance, due to tectonic activity or post-glacial rebound, which effectively changes sea level relative to the land. So, in summary, the oceanographic form of the sea level equation links together three main drivers of sea level change: mass addition, water density change, and land motion. Together, these help scientists interpret satellite measurements of sea level rise in a physically consistent way. This, this slide shows the sea level equation, but in its geographical form. The equation reads S is equal to n minus u. Here, S represents the relative sea level, that is, how high the sea surface is compared to the land at a given location and time. N is the change in the sea surface height, or geode height. This term reflects changes in the ocean's gravitational potential surface, which can vary as mass moves around the Earth. For example, when ice melts or water is redistributed. U here represents the vertical motion of the land, which can either rise or sink due to tectonic processes or post-glacial rebound. So the geographical form essentially says that relative sea level change depends on both how the sea surface moves and how the land itself moves. This form is particularly useful for interpreting measurements from tide gauges, which record sea level relative to the land, not the Earth's center of mass. Here we have the sea level equation, which provides a complete physical description of how sea level responds to the changes in ice mass, water redistribution, and the Earth's deformation and gravity field. Here, S represents the relative sea level variation, meaning how sea level changes compared to the solid Earth's surface. The quantity includes several key components. The first two terms on the right-hand side describe the direct gravitational effects of ice and ocean mass on sea level. The Green's function, shown as G sub S, represents how the Earth's crust and gravitational field respond to a surface load, either from melting ice or redistributed ocean water. The third term ensures mass conservation. It corrects for the total amount of ice that has melted and been added to the ocean. The final two terms, with overbars, indicate global averages, accounting for the overall adjustment of the Earth-ocean system to maintain balance. In simple terms, this equation shows that sea level does not rise uniformly everywhere, Instead, it varies regionally depending on the redistribution of mass, the gravitational pull of ice sheets, and how the solid Earth respond. The full form of the SLE equation is essential for understanding not just global mean sea level rise, but also the complex regional patterns observed. Here are the references, and thank you.